Hello everyone, my name is Xibing. I come from CMIC SGTU China. The title of my paper is Efficient Multicast Schemas in Vehicle Network based on Ruby transform codes. I will introduce this paper from four aspects. The first part is the background. In multicast scenarios, users receive same messages from the base station. However, because of the different channel conditions, the receiving results are various among the users. As the figure shows, errors occur with different quantities, locations, and distributions. To achieve correction, there are mainly two methods to follow. The first is forward error correction method, or called FEC for short, and the second is automatic repeat request, or called ARQ for short. In FEC, systems encode the source messages by error correction code at transmitter and decode them at receiver. In ARQ, the error or missing parts are retransmitted according to the receiver request. But we know the selective transmission to a specific user is inefficient and time-consuming. Therefore, the base station should deliver the retransmission blocks available for all users. There is a simple way named XOR retransmit schema to achieve that. After transmitting the source blocks and then receiving the repeat request from the users, the base station XOR all the source blocks from 1 to 5 and generate the retransmission block 6. Users receive the block 6 and then XOR it with the previous blocks to correct errors. If the errors just limited in one block and the user successfully receives the block 6, like user 1, all the errors can be corrected. User 2 has some mistakes in block 6. He can continue to receive the retransmission block until success. But if errors distribute in more than one blocks, XOR schema is powerless. We can see the advantages of XOR schema is low extra bandwidth requirement and easy to achieve. But when errors occur in multiple blocks, its correction ability is limited. LT code is also based on XOR operation. It will firstly sample a degree from degree distribution, for example 3, then uniformly sample 3 source blocks and get their XOR result. This result is a coded LT block, R1. Then repeat the above two steps. Enough coded blocks can be generated according to the requirement. We see if express the XOR relationships by vectors and concatenate them, the generator matrix of LT code is obtained. The rows and columns respectively represent the source blocks and coded blocks. When having received enough blocks, LT decoder starts to work. If decoding failed, it will receive more blocks until success. Then I will introduce our algorithm. According to the characteristics of LT code, we designed the serial LT code schema, and this is the transmission flowchart. The LT part is to record the source messages, and the LTPC part is to achieve a lower block error rate. The whole multicast process can be divided into two stages. In stage 1, the LT encoder and decoder are unworked. Source messages are delivered to all users in this stage. After transmitting some blocks and receiving the requests from users, the base station enters the stage 2. The LT encoder and decoder start to work. The coded blocks are generated and sent to users for correction. If most users check OK, or enough correction blocks have been sent, the base station comes back to stage 1 and continues to transmit the next messages. In order to intuitively describe this process, we can use the generator matrix of LT code. In stage 1, the coded block is equal to the source block. If missed, the XOR relationship of the block is unknown. Source block is expressed as an all-zero vector. Then LT encoder delivers the correction blocks in stage 2, and users decode these messages with combining the received blocks in stage 1. The decode process is successful if and only if the generator matrix is full rank. In other words, the row vectors in G is independent with each other. We can derive the result from the conditional probability of adding an independent row vector to a full rank matrix. At first, we can add a not all zero row vector. Then, the independent probability after adding the second row is shown as formula 1. Next is after adding the kth row and its parameters. This is a complexity calculation, but if we select about half source blocks to XOR, the formula can be simplified. In these formulas, K is the retransmission number, M is the source blocks number, and epsilon is the block error rate. Serial LT code schema regards the block as a whole. Another way is parallel LT code schema. Through inserted some CRC code in the source blocks, the initial messages are splitted into smaller packets. Then, bit interleaver arrange bit positions to avoid continuous burst errors. We can see the comparison of serial schema and parallel schema process in the figures. We assume the channel conditions are same for these two schemas, so that the block error rate is also same. At that situation, the splitted packets have lower error rates compared to the whole blocks. The relationship between successful correction probability of the two schemas are presented in this equation. The epsilon 0 is the error rate of a single splitted packet, and the epsilon is the error rate of a complete block. We set the source block number M as 100, epsilon equals to 0.1. Then epsilon 0 can be calculated as 0.0011, and we assume the degree is about half of M. To simplify the computation, the simulation result of two schemas is shown in this figure. We can see the curve is almost the same, which strongly proves the relationship equation. Then we will provide the simulation results. We perform the simulation based on the 515 code rate LDPC code and the AWGN channel. The modulation is QPSK. We set the source block number as 1 and 200, block loss rate as 0.4, 0.2, 0.1, and 0.05. For 100 block number, we simulate the average degree at 10, 50, and 90. The simulation results are shown in this table. Be aware of the variable p90% point. It is the k-value when the probability of decoding success equals to 0.9. The variable can measure the retransmission efficiency of the schemas. From the table, we can see the p90% point value is proportional to the block number and the loss rate. Besides, parallel schema has higher efficiency than serial schema at the same condition. At loss rate 0.1, source block number 200, serial schema needs about 15% extra blocks, and the parallel schema only needs less than 5%. The figure shows the successful decoding probability of parallel and serial schemas. The block number is 100, loss rate is 0.1, and the average degree is from 10 to 90. We can see all of the two schemas perform better when average degree is around half of the block number. Users have 90% probability to correct errors after 7 retransmitted blocks in parallel schema and 16 in serial schema. There is a special curve which grows fast and then grows smoothly. It is because the high-degree situation is similar to XOR retransmission schema, so it is more suitable for slight errors, but difficult to correct all. Then is the conclusions. In this paper, we proposed two efficient schemas named serial and parallel LT code schema for multicast system. The detailed processes of derivation and simulation are represented. The results indicate that parallel schema performs better than serial schema when block number is small. But extra bandwidth and system complexity should be considered as trade-off. These two schemas achieve error correction with less retransmission. The multicast system can work with lower latency and higher efficiency. Future works. The derivation in this paper is based on a short-time observation during which blocks number should be small and the channel conditions of users are considered fixed. To approach reality more, the dynamic process on a larger time scale needs to be researched. What's more, the influence of degree distribution can be further analyzed with different conditions, and more multicast simulation results should be provided to compare, and other evaluation standards should be applied. Thanks for watching.